Okay, so hello class, welcome back. So in this recording, we're going to take a look at section 6.1, discrete probability distribution or discrete random variable. So discrete probability distribution are the probability distribution that are designed to model discrete variables. So many of the discrete probability distribution model the counts similar to what we have seen in the previous chapter. So what does it mean by discrete random variable? So before we're going to take a look at the discrete random variable, let's give you the definition of a random variable. So what is a random variable? So a random variable is a numerical measure of the outcome of a probability experiment or a random process. So that's going to be the numerical measure of the outcomes of a probability experiment or a random process. So the values is determined by chance. Okay, so that's going to be the definition for a random variable. So for example, just imagine this, right? So if you're going to flip the coins maybe one times, and then you focus on the numbers of head that might show, right? So the numbers of head that we just focus on the numbers of head, okay? So we don't care about the tail. So if you want to show the numbers of head in that one time that you flip the coin, so the numbers of head could be 0 when you flip a tail, right? So which means the numbers of head could be 0. Or when you flip the head, then the numbers of head could be 1. So that's what they mean by a discrete random variable. It is a numerical measure of the outcome. Yeah, so the outcome tail, we're going to measure that the numbers of head is 0. When the outcomes is head, then we can measure the numbers of heads going to be 1. So that's going to be the numerical measures of the outcome of a probability experiment or a random process. So the values is determined by chance. So random variables are denoted using uppercase letters such as uppercase X. So we're going to use the uppercase letter to name the random variables where the list of the values are written with the lowercase x. So when you list out the values of this random variable x, we're going to show with the lowercase variable, for example, lowercase x. So for example, let's take a look at this example number 1 to give you a better idea of what does it mean by a random variable. So you're gonna toss 4 coins and count the numbers of head, right? So you're gonna toss a coin 4 times and then you keep track of the numbers of head. So let's represent the possible numbers of head in the 4 flip. Okay, so keep in mind we're gonna flip the coin 4 times. So we're gonna keep track the numbers of head. Okay. So what's going to be the possible numbers of head that we might have it? Okay, so we're going to use in the lowercase x to list the possible values of this random variable x, which is the numbers of head in the 4 flip, right? So because we're gonna flip the coin 4 times, so maximum we're gonna get maybe 3 heads in a row. So that's one of the possible case, right? You might have exactly 4 heads in a row, right? So head, 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 right? So that's gonna be 4 heads in a row. Or maybe we're gonna get 3 heads and 1 tail, right? So the numbers of heads could be 3s. Or you might have 2 heads and 2 tails. So the numbers of heads gonna be 2. Or you might have 1 head and then 3 tails. So the numbers of heads would be 1. Or you're gonna get 4 tails in a row, then the numbers of heads could be 0. So I just listed in decreasing order, right? You might rearrange them in ascending order. So x could be 0, x could be 1, x could be 2, x could be 3, so x could be 4. So keep in mind, everyone, so this is x gonna be the numbers of heads in the 4 flip. So maximum, we only do 4 flips, so that's why maximum the numbers of heads gonna be 4. Okay. So that's going to be the random variable. So x is going to be the numbers of head in the 4 flip. Okay. Now consider an experiment that measures the time between arrival, of course, at the drive-through McDonald's could be. The random variable t describes the time between arrival. So this is going to be the random variable t show you the time between arrival. So this is going to be the time, right? So it look like that. Can you give me the examples of this random variable t then? Okay, so t could be any number. So this is the amount of time, right? So watch out for this, right? Because this is the numbers of time. So this is gonna be kind of a continuous random variable. So the only thing that we can say is about this random variables is the amount of time could be some number more than or equal to 0. Yeah, so gonna be maybe some number more than 0 then. So that's gonna be the possible values of this random variable t. Yeah, so it's gonna be the amounts of time. So that's gonna be some number more than 0. We don't know exactly when the next call gonna be arrived, but we know that's gonna be from now until the next I don't know, forever. Yes. So that's gonna be some number more than 0. Yeah. So that's going to be another random variable. So based on the two example 1 and 2, right? So there are some cases we can actually list out the possible values of this random variable, but sometimes it might be have a lot of possible answer for that random variable. So we can classify the random variables as discrete and continuous. I hope that you guys remember the definition of discrete and continuous from chapter 1, right? So there are two different types of random variable we can classify as discrete and continuous. So what is a discrete random variable? So a discrete random variable is a random variable that has either a finite or a countable numbers of possible value. So it must be finite or countable number of possible values. Either has a finite or countable number of possible value. Look like the numbers of head in the fourth flip right here, right? So it's gonna be finite, right? Yeah, so that can be finite, so we can actually keep track and we can count it. Oh, 0 head, 1 head, 2 head, 3 heads, 4 heads. Okay. So finite numbers of values such as 0, 1, 2, 3, 4, or a countable numbers of values such as 1, 2, 3, 4, and etc. So that's gonna be discrete. Yeah, so discrete gonna be finite or countable. Now, on the other hand, we're gonna get continuous random variables. So a continuous random variable has infinite many values. It has infinite many values that are uncountables and measurables, right? So they're going to be measurable. So if you remember the definition from chapter 1, most of the time the variable that we come from the measurement, that's going to be continuous. Yeah, so continuous variables. So a continuous random variable kind of similar. It either has infinite many possible values or uncountables or measurables. So a values of the continuous random variable can be plotted on a number line in an uninterrupted fashion. So this is an examples of the continuous random variable, gonna be any number from zeros and more. Okay. So that's gonna be the definition for discrete and continuous. So once again, discrete gonna be finite, countable. Continuous gonna be infinitely, is uncountable and measurable. So that's gonna be the definition for these discrete and continuous random variables. So now let's give it a try, everyone. Let's take a look at the next example. Let's see if you can identify if they are discrete or continuous. So example number 3 determines if the following random variables are discrete or continuous. Yeah, so state the possible values of the random variable. So question A, we talk about the numbers of light bulbs that get burned out. Okay. In a room of 10, yeah, so the numbers of light bulbs that got burned out in a room of 10 of them in the next year. So this is the numbers of light bulbs right here, right? So are they discrete or continuous? Can you actually count it? Are they finite or they are infinitely? So this is the numbers of light bulbs that are gonna get burned out, right? In a room that have tens of them. So actually we can really count it. So this number is countable, right? Or it's gonna be finite, okay? So I'm gonna say this is gonna be discrete random variable. So that's gonna be discrete random variables, yeah. And what are the possible values of this, the numbers of light bulbs I'm gonna use in the variable B then. So what's the possible values of this variable, which is the numbers of light bulbs that's gonna get burned out in a room of 10 of them, right? So the numbers of light bulbs gonna get burned out could be 0 when none of them gonna get burned out, right? Or could be 1 of them, or could be 2, could be 3, could be 4, could be 5, could be 6, 7, 8, 9, or on the way up to 10. because we have maximum 10 live balls. So that's why maybe maximum on 10 of them gonna get burned out. Yeah, so that's the possible value for this random variables. Now question number B, the number of free throw attempts. Yeah, so this is the numbers of free attempt. The numbers of attempt before the first shot made it. Okay, so it is gonna be discrete or continuous. Yeah, okay. So the numbers of free attempt before the first shot is made it. Okay, so what you think is that gonna be discrete or continuous? The answer will be discrete because this is countable, right? So you can really sit down and keep track of the numbers of attempts that this person gonna do until the first shot is made. I know that maybe some of the cases might take forever, but actually it's countable, right? It's countable, so you can actually sit down and we can count it. Yeah. So that's gonna be discrete, random variables. And then the possible value for the numbers of attempt I can use in the variable A. So A could be 1, 2, 3, 4, 5. And then in this case, I'm gonna use in dot, dot, dot. I'm not gonna know where it's gonna stop. So that's gonna be countables, yeah. So this is a discrete random variables, and there's gonna be countables, right? Yeah, so now the amounts of rain in LA during February, right? So what's the amounts of rain? Okay, so the amounts of rain right here, is that gonna be finite or infinite? Okay, so the amounts of rain right here is gonna come from the measurements, right? So this is gonna be continuous. Yeah, so continuous. And then what's the possible value for the amounts of rain or? Okay, so gonna be some numbers more than or equal to 0. Yeah, so that's the only thing that we know. So the amounts of rain could be none or gonna be some number more than that, right? So the amounts of rain is gonna be continuous. Yeah. So the numbers of live ball got burned out in a room of 10 of them, that's gonna be discrete. The numbers of free attempt until the first shot is made is gonna be discrete, and then the amounts of rain in LA is gonna be continuous. Yeah. So that's going to be the sum of the example to give you the better ideas of the discrete and continuous random variable. So after we know that a random variable is either discrete, then we're going to do further summarization of this one, right? So we're going to talk about the probability distribution. So what is a probability distribution for this discrete random variables? So the probability distribution of a discrete random variable x provide the possible values of that x. Okay, so we're gonna list the possible values of that x with their corresponding probabilities, and then with their corresponding probabilities. So the second column, we're gonna show the corresponding probability. So we're gonna show the possible values of the random variable x on one of the columns or one of the rows. And then the second column or row, we're going to show the corresponding probabilities. The distribution could be in the forms of a tables, a graph, or some math formulas. Okay, so that's how we show the probability distributions. Yeah. So let's give it a try for this example. So you're going to toss 3 coins. Okay, so you're going to toss 3 coins and count the numbers of heads. So keep in mind, we only do the 3 toss of the coins right here, and we count the numbers of heads. So the numbers of heads in the three times that you flip the coins is gonna be discrete random variables. So we're gonna let x represent the possible numbers of x. So x gonna be the possible numbers of heads. I'm sorry. Yeah, so x gonna be the possible numbers of heads in the 3 flip. So keep in mind, everyone, we only do 3 flips. So maximum we might have 3 heads in a row. Construct a probability distribution for this random variable x. Okay, so now before we can come up with the probability distribution, so let's see what's going to be the sample space for these distributions. Okay, so based on these rule that we learned from chapter 5, right? So we might use the multiplication rule to determine the sample space. So when you toss a coin 3 times, there are 8 possible outcomes. The first one had 2, the second one had 2, the third one had 2. So we multiply those numbers together. 2 times 2 times 2, that's how we're going to get 8 possible outcomes, okay? So now I'm going to list the 8 possible outcomes to see what is it then, okay? So in 3 times that you flip the coin, right, there maybe all of them gonna be tail. So you might have tail, tail, tail look like this. Or you might have tail, head, head. Or you might have head, tail, head. Or you might have head, 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 and tail. Okay. Now you might have something look like this, tail, tail, head, like this, right? Or tail, head, tails, or maybe head, tail, tails, right? Okay. Okay, now how about the next one? So you might have head, head, head. There you go. Okay, so those are the 8 possible outcome, right? So let's double check 2, 4, 6, 8. Now let's do some analysis based on those possible outcome, right? So for the first outcome right here, what gonna be the possible, what's the numbers of head in this outcome? So for this outcome right here, right? So we can see the numbers of heads gonna be 0 because none of them are head, right? So tail, tail, tail. So which means that the numbers of head in this possible outcomes is 0. So I'm gonna list a 0 but now for the next case right here, for the next group of possible outcome, we see what gonna be the numbers of head in those outcomes. So in each of those outcomes right here, we can see that for each of the outcome, they're gonna show exactly 2 heads, right? So I'm gonna put a 2 right here. Now I'm gonna take a look at the next group of the 3 outcome right here, right? So this is gonna be the next group of the 3 outcome we're gonna take a look. So now when you take a look at each individual's outcome right here, right? So how many heads we have in there in each of the possible outcome. So this gave you 1 head right here, right? So in each of those outcomes, they gave you exactly 1 head. And then for the last case right here, we can see this outcome gave you exactly 3 heads, okay? So the possible number values of head in the 3 times that you flip could be 0, could be 1, could be 2, could be 3. Maximum gonna be 3 because we only do 3 flip. Okay, so maximum we might have 3 heads in a row. So that's gonna be the possible values of the random variable x. So now after we got a possible random variable, now we need to show the probability. So what's gonna be the probability for you to have exactly 0 head? So what is the possibility that's gonna give you exactly 0 head? So 0 head, which means the case we're gonna get tail, tail, tail right here, right? So there is exactly 1 possible outcome out of the total 8 possible outcome. So the probability will be 1/8. Now, similar idea, what is the probability that you will have exactly 1 head? So exactly 1 head is equal to 3. So there are 3 possible outcomes that's going to give you exactly 1 head. So the numbers of head in this, the probability will be 3/8. Okay. So there are 3 possible outcomes that's going to give you exactly 1 head. Now, similar idea, what is the probability that you will have exactly 2 head in the 3 flip? So exactly 2 heads, we're going to take a look at those outcomes right here, right? So in those possible outcomes, we can see that there are exactly 2 heads, right? So the probability that you will have exactly 2 heads in the 3 times that you flip the coin will be 3/8. Now the last case, what's the probability that you're going to have 3 heads in a row in the 3 times that you flip? So only 1 possibility is heads, heads, heads. So the probability will be 1/8. So this is a probability distribution that gives you the so that's gonna be the probability distributions. Yeah. Okay, so I hope you guys doing okay with this, right? So that's the probability distribution. Now, because this is a probability, right? So this is a distribution, but in this distribution, we have the probabilities, right? So that's why the rule for the probability that we have earlier is to work with these probabilities. Yeah. So what's going to be the rule that we may apply for the discrete probability distribution? So the rule that we have for discrete probability distribution is similar with the rule that we have for the probability that we learned from chapter 5. So let Px denote the probability that the random variable x equal x. So the random variable x equal x. Then the summation for one of the probability Px equal 1. The summation for one of the probabilities of Px is going to be equal 1. So we can double check that condition, right? So 1/8 plus 3 over 8. So 1 divided by 8 plus 3 divided by 8 plus 3 divided by 8 plus 1 divided by 8. So the summation for all of the probabilities when x equal x gonna be equal 1. Let's double check this. So the total is equal 1. That's good. So that's the first rule for the probability. The second rule for the discrete probabilities is the individual values of px is between 0s and 1. So 1 over 8 between 0s and 1. 3 over 8 between 0s and 1. 1 over 8 between 0s and 1. So that's good. So that's going to be the rule for the discrete probability distribution. It's similar with the rule for the probability distribution that we learned from chapter 5. Yeah. Now let's use these ideas, everyone, to determine if which of the following tables is a discrete probability distribution. So we have the 3 tables right here, right? Now we're going to determine which one of them going to be a discrete probability distribution. Is that the first one, the second one, or the third one, right? Okay. So we're going to use in the property that the rule for the discrete probability to double check, right? So for the first tables, you want to make sure that the summation for all of the px right here should be equal 1. So let's give it a try. The summation for all of the px, right? So it's going to be 0.16 plus 0.18 plus 0.22 plus 0.10 plus 0.30 plus 0.01. Okay. So let's double check if the sum of those equal 0 or equal 1. Yeah. The summation form of the px right here is which is equal 0.97 and not equal 1. So unfortunately, this is not a probability distribution. So let me show that. The summation for all of the px is equal 0.97, not equal 1. Yeah. So the summation for all of the px equal 0.97, which is not equal 1. So it's failed. Okay. So this is not, yeah. So this is not a probability, or more specifically, this is not a discrete probability distributions. Yeah. So because the first condition, we check it and it's failed, right? So that's not good. So the first condition already failed. So that's why this is not a probability distributions. Okay. Now let's take a look at the second table. Is this a probability distribution or is this a discrete probability distribution? Let's take a look at the second table. So now the first condition, let's double check, right? So the first condition, 0.16 plus 0.18 plus 0.22 plus 0.10 plus 0.30 plus negative 0.01. That's not equal. Yeah. 0.16, 0.18, 0.22, 0.10, 0.30. 0.30 and negative 0.01. Okay, so once again, the total right here is not equal 1. Okay, unfortunately, the total right here is not equal 1, so that's not good. Okay. So which is 0.95? That's what we got right here, not equal 1. So no, this is not, yeah. So this is not a probability distributions, or it's going to be discrete, yeah. I'm going to say this is not a discrete. To get the answer more precise, so this is not a discrete probability distribution because the summation form of the px right here is not equal 1. Okay. And then in addition to that, we have the last possible values of px right here, right? So when x equals 5, the probability is a negative 0.01. That's not good. Okay. Now, how about the third table then? Okay, so let's double check the first condition. Let's see if the totals equal 1. Okay. Let's double check to see if the totals equal 1. We will see. Let's add them up first. So 0.16 plus 0.18 plus 0.22 plus 0.10 plus 0.30 plus 0.04. Okay. Okay, so the total exactly is equal 1. That's good. So it's equal 1. That's good. The first condition is true. How about the second condition then? So when you double check the individual values of px, it should be between 0s and 1. That's good also, right? Yes. So all of those values that we have for the px right here between 0s and 1. So the first condition, check. The second condition also check. So yes, this is a discrete. Yeah, so just a discrete probability distributions. Yeah. Okay, so that's how we determine if we have a discrete probability distributions. Okay. So make sure that you're using the two rules that we have for the probability distribution, right? The summation form of the px is going to be exactly is equal 1. The individual values of px between 0s and 1. Okay. So that's going to be how we determine a discrete probability distributions. Okay. Now, after we got the discrete probability distribution, now we're going to take a look at this histogram, right? So based on the discrete probability distribution, we might present it in a picture, a histogram, right? So we visualize present this table by using the histogram, okay? So how we're going to do the probability histogram? So a probability histogram is a histogram where the horizontal axis corresponds to the possible values of x. So on the horizontal, we show the possible values of x. So the horizontal axis is going to be corresponding to the possible values of the random variable x. So going to be x1, x2, x3, x4, x5. And the vertical going to show you the probabilities of those values p, xi. So the vertical is going to show you the probabilities. So a probability histogram is similar to the relative frequency histogram, but display the probabilities instead. So when you do the probability histogram, it's going to be similar with the frequency histogram. So that's what we learned from chapter 2, right? So for the relative frequency histogram on the vertical axis, we show the relative frequency. But this is a probability histogram, so that's why on the vertical axis, we're going to show the probabilities instead. Yeah. Now we're going to take a look at the table that we have earlier. Now we're going to do this histogram. So draw the probability histogram of the probability distribution below, which represent the numbers of movies streamed on a popular platform each month. So the numbers of movies got streamed could be 0, 1, 2, 3, 4, 5. And the corresponding probability is going to be 0.06, 0.58, 0.22, 0.10, 0.03, and then 0.01. Okay. So now I'm going to put the x values on the horizontal axis. Yeah, so I'm going to put a 0. I might shift the origin, the zeros on the horizontal a little bit to the left right here, look like this case. So I'm going to start with the 0, 1, 2, 3, 4, 5. That's good enough. I just add a 6 right there. Now on the vertical axis, I'm going to show the corresponding probability. So based on my observation right here, the maximum values I'm going to show is 0.58. So on the vertical scale, I'm going to show the 0.10. So I'm going to get every increment on the vertical is going to be 0.10. So we're going to get 0.10, 0.20, 0.30, 0.40, 0.50, and 0.60. So around there, approximately. So now I'm going to draw the first rectangle. So my first rectangle, I'm going to center it at 0, half unit to the left and half unit to the right. Okay, so I'm going to draw the first rectangle, center it at 0 with the relative frequencies of 0.06 or the probabilities of 0.6. Yeah, 0.06. So going to be a little bit more than halfway. So it's going to be something look like this. Okay. Okay. Now, so I'm going to draw the maybe it's too high, right? So you can make it a little bit smaller. Yeah. So make sure I show the 0.06. Okay. Now the next values when x equal 1, you have 0.58. Okay. So 0.58 look like all the way up to 0.6, right? So this is 0.10, 0.20, 0.30, 0.40, 0.50, 0.60. So a little bit lower. So I'm gonna do approximation, everyone. Don't pause me on this, right? So it's gonna be half unit to the left, half unit to the right. Okay. Maybe this rectangle is too big, so I need to shift the unit over. Let me move it right here. Okay, let me skip this one. Maybe the 2 gonna be right here, and the next one gonna be 3. We'll see if this works. Yeah. Now, when x equal 2, we're gonna get 0.22. Okay, so when x equal 2, we have 0.22, so this is gonna be 0.10, 0.20, 0.22, a little bit higher, so it's gonna be something like this. Now, when x equal 3, we're gonna get exactly 0.10. When x equal 4, we have 0.03. 0.03, so that's gonna be half. Go. And when x equal 5, we don't need 6 then. 0.01. Maybe just something like this. I wanted approximately. It's okay. There we go. Okay, so that's gonna be the histogram, probability histogram. Okay. So based on this calculation right here, we can actually determine the distribution, right? So based on the histogram right here, we can say that, oh, look like the distribution will be skewed to the right. Okay, so this can be skewed to the right. Okay, so the tail is longer to the right, so that's why we can say that's going to be skewed to the right. So let me try to connect the rectangle together so it can give you a better idea. How can I know that's going to be skewed to the right? Yeah. So something like this. Okay. So I just tried to connect the rectangle together, and we can see that look like the tail to the right is going to be longer. So we can say that the distribution of this random variable will be skewed to the right. Okay. So that's the histogram, right? So the probability histogram. Okay. So we just talk about the definition of the random variable. We talk about the probability. We talk about discrete random variables also. We talk about the probability distribution, and we talk about the presentation, a visual way to show the probability distribution. We see the histogram. Yeah, so this is gonna be the histogram, or to be more specifically, you can say this is gonna be a discrete probabilities histogram. Okay. So I think I'm gonna stop the recording at this point to give you the half of this section 6.1. Okay, so I'm going to stop the recording up this point, everyone. This is the first half of section 6.1. I will see you next time for the second half of 6.1.